Hey everyone, this is Manshark Sub LPs. I'm Sub, and this is Odyssey, the Invention of Science. We have just learned about Aristotle, Ptolemy, and Copernicus, and I think we're about to continue learning about it in this room here. Yep, so there's a box there, which no doubt contains a journal. Looks like the Earth and the Moon, if I had to guess. Or is it the Earth and Mars? Okay, we're going to be looking at whether Mars rotates around the Earth or orbits around an object too. Okay, this should be fun. Yep. Okay, so it looks like it saves when we pick up a journal, so that's good because this is... I'm not going to record another episode after this one today because, I can feel my voice starting to go. There's a lot of reading in this game. Also, you know. Mars. July 25th. Where are these pirates? It's been almost 2 months since they started. Apart from Jupiter, Mars is another planet that's clearly visible in the night sky. I've looked at Mars through the telescope a few times, but it just turns a slightly reddish dot into a slightly bigger reddish disk, with nothing much else interesting about it. Tell that to Elon. It didn't help with my geocentrism, heliocentrism debate anyway. Dad said that might not be true, if I had a lot more time to observe it. He says Mars was going through an unusual period now. Normally, like the Sun and the Moon, planets appear to travel through the Zodiac constellations. That's why those astrologer, like, the scam artists can be all like, oh, Mars is in whatever, or Neptune in Gemini, so like that sort of stuff. And normally, like the Sun and the Moon, planets appear to travel through the Zodiac constellations. The Sun progresses through the Zodiac constellations in the order they appear around the ecliptic, but sometimes planets stop and move backwards through the Zodiac. For Mars, this was one of those times. Mars was currently in the constellation Sagittarius, and if it moved through the constellations like the Sun does, it should be moving towards Capricorn, but instead it was moving back towards Scorpio. Dad said, in a few weeks it will stop and go forward again to Capricorn. Dad said this temporary backward or retrograde motion of Mars was a problem for ancient astronomers. A model that put Mars on a spinning celestial sphere, like the Sun, couldn't explain it. I asked Dad what Ptolemy thought about this, since it contradicted his beliefs that bodies made of ether in the celestial realm have to keep moving in perfect circles. Mars retrograde motion. Yeah, it sort of does that. Cool. Dad said it was tricky to explain, but at lunchtime he'd use a model to show me how it worked. Dad said a simple way to make Mars orbit the Earth was to make it trace a circular path around it. But since the ancient astronomers knew about retrograde motion, they had to make Mars go backwards sometimes without violating the requirement that everything must always go in the same speed in the same direction along the circle. According to Dad, an ancient astronomer named Apollonius, here's Apollonius here, he's got a beard, he can be trusted, came up with an ingenious way to meet this requirement, and Ptolemy adopted it. Yeah, so he made something up. No, really? Apollonius showed how the overall trajectory of Mars could look like it does, not a simple circle, but as a combination of two paths, where each of them were perfect circles being traced at constant speeds. I really couldn't understand what Dad meant by this. So we got Dad's Buddha board from the bunker at lunch. Here's the Buddha board. He likes using it to paint quick sketches using only water, and soon the sketch disappears as the water evaporates, so we can reuse the board and not need any paint. He set up the board on top of a table in the hut, but he rigged it with two motors, one that spun an axle at the center, with a long arm attached, and another that spun a smaller arm around the end of the long arm. He put a paintbrush at the end of a small arm, and he said it represented Mars, with Earth at the center of the board. The long arm traveling in a big circle, like the main orbit of a planet, Dad called a deferent. The other shorter arm, which goes in a smaller circle, Dad called an epicycle. He then showed me how Mars could be made to go around a small cycle, the epicycle, while the center of the epicycle goes around the larger circle, the deferent, with the Earth at the center. By adjusting the two speeds of motion along the epicycle and deferent, you could have Mars, that's a much better picture of it, have Mars sometimes reverse and go backwards like the retrograde motion we see in the sky. I paused the arms at the moment Dad was moving backward in retrograde to show Dad, and he said I was right. Yeah, so basically the idea is if you're looking at Mars, Mars isn't going around like this. Mars is going in like... Mars is orbiting something which is orbiting Earth, which is exactly what they said couldn't be the thing with the moon. That the moon couldn't orbit Earth if the Earth orbited the sun. Because because it would add another layer of complexity. This is literally adding another layer of complexity for special pleading, again. This might sound bizarre, but playing with the spinning arms on Buddha board, I could make lots of unexpected and beautiful patterns just by changing the speeds of the epicycle and deferent. It wasn't just a model, it was a fun and great art tool. I wish I could show this to everyone at school. We've got some patterns that they made. Yeah, if you adjust the speed that this goes in relation to the speed that this goes, it gets a lot, like you can do amazing things. I'm almost sad, but I have to show how this beautiful tool is wrong about the way the universe works. And if you do it like at the same rotational speed, I think you can get like a off-center circle. In Ptolemy's model, the Earth is fixed, so it's easier to figure out how things would look from Earth since it's not moving. The outer celestial sphere of stars rotates once a day. Planets do that too, except they move relative to the stars. Dad simplified his model by ignoring the daily rotations because retrograde motion isn't something you see in a single night or day anyway. To show retrograde motion with the sun at the center, I needed to build a model that could visualize where Mars would be in the sky when Mars and Earth were both moving. I also ignored the diurnal rotation of the Earth, like Dad did, since it makes no difference. Fortunately, the stars don't move in my model, so at least something can stay still. The stars are fixed in the sky, so I decided to build my model in the bottom of a cut-off barrel like my other model, painting the Zodiac constellations on the inside rim, as seen here. First, I mounted a fixed light bulb on the bottom of the barrel in the center to be the sun. Then Sid helped me make two rotating arms, a short one to hold a model of the Earth, and a longer one for Mars. We also rigged a pen laser beam. That's like 3 laser beams you've used so far. Do you have like a crate of these things? On the Earth, so it would always point at Mars, no matter where both planets were. But then I made a wide tunnel through Mars, so the laser could pass through and hit the stars painted on the barrel, to show where Mars would be on the Zodiac as seen from Earth. The last thing was deciding what speeds the planets would move. Dad gave me a hint, but in Copernicus's model, the revolution speeds around the Sun decreased the farther away you were. Mercury was the fastest, Venus less fast, Earth even slower, and finally the stars were stationary. That sounds like another elegant pattern to me. Not that elegance is most important, of course. That was really a problem with like classical scholars and philosophers where they tried to find an elegant explanation. Finally, it was done, and I played with the speed of both planets, making Earth go around the Sun in less time than Mars took, and boy did I get a shock. The laser beam moved the Zodiac constellations in the correct order, like we would see from Earth. Whenever the Earth caught up with Mars in their orbits and passed by, the beam would temporarily move backwards. I can even pause it to show Dad that later the moment it happens. It's awesome! The retrograde motion of Mars literally emerged out of a model, and without any complications like epicycles and deferents, without even knowing how it would happen while we were building it. Really hanging out for these pirates. How big is this book? I explained to Dad at dinner how my heliocentric model could explain the retrograde motion of Mars in a simpler way than the geocentric model, because it required no far-fetched features like epicycles. Dad said he was very proud of how I discovered retrograde motion emerging naturally from my heliocentric model, but it didn't prove Ptolemy was wrong. Okay, it didn't prove it, but it was so much better and simpler. But then Dad said it turns out Copernicus's model didn't match observed locations of stars and planets as well as Ptolemy's model did. Not until Copernicus introduced his own own epicycles, so that when the models were done carefully enough to match what we saw in the sky, was Copernicus's model really simpler? And then Dad said even if it was, it doesn't matter, because simpler doesn't mean true. That's fair. Occam's razor doesn't dictate truth, it dictates likelihood of truth. I could tell Dad felt bad about how discouraged I was, but he said truth is truth. Nature doesn't have to appear beautiful or elegant or simple to humans. Maybe it was to cheer me up, but Mum said it was time for us to drain the water from the lagoon at the base of the stairs. Yeah, nothing gets me more cheered up than environmental destruction. She sent Sid and Guillaume to the boat to get the sump pump and enough solar cells to run it, but we'll have to time it right first thing in the morning, starting a few hours after high tide, to drain the lagoon and still have time to see if the army door down there can open and explore what's in there and safely return before high tide comes and floods the lagoon again. Okay, so clearly what we're trying to do here is so it goes up to there and back around. Again, we could literally just hook it straight up to the pump. We don't need this puzzle bullshit. Okay. So what are we trying to actually get here? We need this one to get power to that one first. So we're doing something on this one. Hang on. Okay, we're adjusting rotational speeds and epicycles. Hey, this will actually help us out. Yep, so let's put in a nice slow. I want it to make it at least a full circle. So here's our. I've already forgotten what they call it. But if we stop it and then increase this one, see these are the epicycles. So what I actually want to do is I want to put this on like the halfway point there. Sorry, fuck that up. And we want to get this one rotating again. Okay. So let's play around with this. I know what it wants me to do. It wants me to actually properly simulate the epicycle thing. But what I want to do is see if I can get it so that it creates a proper... Actually, if we just match them, so 118... So 119... 119, there we go. It's not quite exact because I'm having trouble getting it quite exact. So 119.3... 119.1. Yeah, I'd imagine if we could get it correct. See, this is forming the same shape every time. But it's sort of, it's an off-center circle. Now if I halve this one down to say 60, yeah. So what this does is it makes the smaller side of the circle on this side, the largest. Is that doing what I think it's doing? Oh, it goes one small, one big. Okay, that's cool. What if we put it down to 30? Does that do what I actually want it to do now? No. Okay, what if we put this one down to 60 and this one back to 120? Okay, this is going to create a little egg shape for us. So this one again down to 30, and this should create like a four-lobed structure. Yeah, see, you're beginning to see the sort of lobes appear that it was after. Let's speed this right up to say 240. I mean, that's pretty close to what we're thinking. And if you speed it like right up and you get this sort of weirdness. I'm not 100% sure what they're trying to get us to do. So let's have another look at the journal. Yeah, that's the next one. This is what we're looking for here. Adjusting for two speeds of motion. Different was the thing. Okay, reverse. I paused the arms at the moment Mars was moving backward in retrograde. Okay. So let's... Done. Alright, now we've got to figure this one out. Oh yeah, so go. You know, it actually took a lot more effort for this, which is weird. Having it so that the laser is always lined up at Mars. That would have taken a lot more effort than getting them to rotate. Okay, let's go down to the beach, or to the lagoon, and drain it. Yeah, so here's our lagoon. So high tide must come up like a fair way. Yeah. Get wrecked, water. Hey, it is actually going down. I thought they might just replace it. Cool. Okay, what has this damn kid done this time? I see the papers. We'll get them in a second. Really want to know where these pirates are, though. About an hour past high tide this morning, the alarm drained the little lagoon at the base of the stairs of a sump pump. It was designed to pump out the boat in case we took on water. I mean, that's what a sump pump is, yep. But Mum doesn't like to take any chances, so she got a super strong one. It emptied the lagoon in no time. Galam and Dad needed to use a crowbar and pull together. We managed to break through the rust and open the door. Inside was a cave leading to an underground grotto. There was a mining cart and some metal rails and sacked wood and a pickaxe. Like this was a storage area for things needed to dig tunnels and lay tracks. There wasn't much left, so Sid and I wonder if the army took most of it when they left, or if we'll find more tracks and caves once we get to the rest of the islands. There's a small bridge leading over the grotto. Mum said it's ironic that the one bridge we don't need is the one that isn't wrecked. It was also built to go up and down, so maybe so the army could raise it from the other side for protection, like the rotating bridges outside. And just like in the bunker, Mum wants a way to get in if she needs to, so she says she'll rig up a linkage to drop the bridge from the lagoon side. On the other side of the grotto are some old tables and some empty bottles. But don't worry, Dad, because it was obvious they were old from the army days. The best part is there's a switch that triggers a drop ladder leading up to the base of a radio tower. The tower ladders were still intact, and Sid and I got to the top in no time. Her ankle must have healed by now. We have a great view of the rest of the islands. I even think it would be the perfect place to put the telescope, but the high tide will flood the lagoon soon, so it's not practical. Still, it's pretty cool up here. It turns out high tide doesn't refill the grotto. Hey, isn't that convenient? The water level gets high enough for waves to sometimes splash over, so it might refill in a few weeks, but the sump pump easily keeps up with the amount of water that spills in. Once we saw that, the first thing Sid and I did was mount the telescope at the top of the radio tower. I can hardly wait to try it out tonight. In the meantime, I was thinking about differences between the heliocentric and geocentric models, and I realized that with my heliocentric model, there's no need for the stars to be stuck on a sphere. The original reason the geocentric astronomers put them on a sphere was so the rotation of the sphere made all the stars move in synchrony. But if Earth itself spun around its excuse me, flub that sentence. But if Earth itself spun around its axis, there's no need for the stationary stars to be on a sphere or all the same distance from us. In the heliocentric model, the stars might as well all be different distances away. Dad asked me how this might affect the missing parallax effect of stars we talked about before. In that experiment, when measuring how far apart Dad's arms looked compared to each other, They were both the same distance away from me. What if one was closer to me than the other? And what if I moved in other directions, like sideways instead of forward and back? When I tried it in the shack, trying to focus on different things, like tables and windows, it was too confusing. Then it occurred to me I could make a model of the sky down in the grotto where it's really dark. I could hang different coloured LEDs, like stars, at all sorts of different distances, and see if I could figure out how the lights were arranged just by moving around. I asked Sid to hang lights all around. We used the retractable bridge to get him up to the ceiling of the cave, and I didn't watch, to keep from knowing where all the lights were. Then he came down and we turned them on. I wanted to be precise, so Sid and I set up some tracks to slide in the mining cart back and forth. By shifting my position sideways, I saw that stars closer to me shift more than stars which were further away. This not only changed how far apart they seemed, but some had actually changed their relative order from left to right, as seen here. Like, star A was to the left of star B from one vantage point, but going to another vantage point, star A moved to the right of star B. Come to think of it, this is like driving on a freeway, where trees up close zip by faster than distant mountains, which move slowly. It was really cool, and I asked Dad if this was something anyone saw with real stars. With the driving example, maybe she should have realized that she's the one moving, not the trees or the mountains. He said scientists can measure tiny differences now, but back then no one could detect any changes in the relative distances between stars, even across 6 months when Earth moved the greatest distance, because they could never see any change, no matter where Earth was. They said this proved we must be stationary. I said again but this wasn't convincing if the stars are really far away, and it seems like they are, so seeing no parallax didn't disprove heliocentrism. Dad agreed that it didn't definitely disprove heliocentrism, but it didn't prove it either, so I still had to find more evidence. Pictured here, the evidence. Mum says there's lots more work to be done to secure all the bridges better later, but we might get the next one repaired enough to rotate it and safely move across to the next chunk of Retrograde Minor by tomorrow. That would be great! I've explored what I can, and I'm ready to see more of the islands. Only I haven't been keeping up with my sunscreen, and got sunburned, so Mum wants me to stay out of the sun today. I'm really talked too much for the last 2.5 hours. I'm excited about exploring the rest of Wretched Minor soon, but I told Dad this morning I was about to give up on trying to prove heliocentrism. I looked at the stars, the sun, the moon, and the planets Jupiter and Mars. But apart from poking a few holes in Aristotle's ideas, I couldn't prove Earth revolves around the sun instead of the other way around. I understand both models better, which Dad says is good all by itself, but I couldn't find any way to prove my case. I asked Dad at lunch if there are other planets we could see with a telescope. He said I could see Venus, but I'd have to get up just before sunrise because Venus never strays far from the sun. I asked if he meant that Venus never gets high in the night sky like Mars and Jupiter, and he said yes. Venus can be seen just before sunrise, when it's often called the morning star, or just after sunset, when it's called the evening star. Yeah, there's a good reason for this. He said the same is true of Mercury. Both planets are always close to the sun. That's why Ptolemy believed Venus and Mercury had virtually the same relative orbital speed as the sun around the Earth. I wondered how the heliocentric model would deal with this. Jeez. Since I was shut in all day, I spent the afternoon building a model with the sun in the center and Venus going around it. When I finished, it was easy to see why Venus never appears far from the sun, because Venus is an inner planet, and its orbit around the sun is smaller than the Earth's. Literally whenever you look at Venus, you're always looking at the sun. So whenever we look at Venus, we're always looking approximately in the same direction as the sun. That's why Venus can only be seen around the times when the sun sets or rises. This would be more true of Mercury, since its orbit is smaller than Venus, so it must always be even closer to the sun. I asked Dad why Mercury is invisible now, and he said it currently happened to be directly in front of the sun. I told Dad the heliocentric model automatically explains why Venus and Mercury stay close to the sun, without needing to give them all carefully similar orbital periods like Ptolemy's model required. This is another way my model is simpler. He agreed, but reminded me that simpler isn't necessarily true. I still didn't have proof. Oh geez, I thought we were at the end because there's this huge blank spot here. Right, cool. June 28. Pirates. I crawled into my sleeping bag to go to sleep early, to get up before sunrise and see Venus. But then I got an idea. While playing with my Venus model today, I noticed that as it orbited the sun, Venus went through phases just like the moon. I didn't think about it much at the time, I just wondered what phase Venus would be in tomorrow. But now I just realized that in Ptolemy's model, Venus never goes behind the sun, and it never gets far from the sun. It means it will always be more or less between Earth and the sun. If that's true, then we would only ever be able to see Venus in a crescent phase. That means if I see Venus tomorrow morning in the full phase, or close to it, that would definitely prove Ptolemy's model is wrong. But you see, Kai, you haven't considered Ptolemy's introduction of some weird lighting system on Venus, which just happens to make it all work. I knew Dad wouldn't tell me I was right. He'd want me to see for myself. So I casually asked him which phases we can see Venus go through when we observe it from Earth. He just smiled and said I could see it for myself if I just went to sleep, but I don't think that will happen anytime soon. July 29. I had a hard time getting to sleep. Mum thought it might be the breeze, so I moved from the porch to inside the shack below the zip line. Next thing I knew, Dad was waking me up. It was still dark as we worked our way through the grotto and up the radio tower to the telescope. The eastern sky was already getting light and the stars were fading, but Venus stayed bright, pictured here, until it was the only dot of light in the sky. I could see why it's called the morning star. I lined up a telescope and looked at Venus magnified. It was still small, but I could clearly see that it was fully round of the bottom half, in the direction where the rising sun would appear, as seen here, and a bit squashed on the top half away from the sun. It looked just like the moon when it was almost, but not quite full. That's it! This proves Venus orbits the sun. I told Dad to look and see, but he couldn't because I was jumping up and down and it was wiggling the radio tower too much. When I stopped, he could see it, and he gave me a big hug. Yes, I approve Ptolemy's model is wrong. Suck it, Greeks! Dad said he was very happy because I had rediscovered the astronomical findings of another famous astronomer named Galileo. Wait, was Ptolemy Greek or Roman? I think he was Greek. Also using telescopes, Galileo defended Copernicus's model with the same astronomical discoveries I made this week. Here's Galileo. Again, you can trust him because he's got a beard. When the sun came up, we climbed down to look at my Venus model again. It explained why Venus showed all the phases and always stayed close to the sun. Looking at it, I also realized that when Venus is full, it's a lot further away from Earth than when it's a crescent. If I looked at Venus again months from now, would the crescent Venus look a lot bigger than the full Venus? That would be even more proof, because Ptolemy's geocentric model always had Venus the same distance from Earth, so it should never change size. But you've forgotten. It's probably on one of his epicycle phases. Dad said I'd have to wait a few months to check. I howled and he said he was just kidding. Yes, the crescent Venus looks bigger than the full Venus. Galileo also used this to argue in favor of Copernicus's model. I'm really glad Dad didn't make me wait this time to see for myself. I'm going to make another track for my Venus model, curving the other direction, so I can switch between the full circle heliocentric track to a second track, which shows Venus as it would look going around Earth, with the sun always behind it. This new geocentric track doesn't need to be very long in either direction, because Ptolemy's model kept Venus near the sun. I'll do it later. The important part I already have, where I can position Venus on the far side of the sun to show it in full phase, to contradict Ptolemy's geocentric model. Again, suck it, Greek philosophers. July 29. Dad let me enjoy the pleasure of disproving Ptolemy's geocentric model of the universe for almost a whole hour. Then at breakfast, he told me that I had proved geocentrism wrong, but I hadn't proven heliocentrism was right. That made no sense. It had to be one or the other. He laughed and said he was making a joke, but also not really. He said I proved Aristotle and Ptolemy were wrong about geocentrism, but they had arguments about heliocentrism, but I hadn't refuted because Dad hadn't told me about them yet. Wow, Dad's getting into a real right-wing grift debate lord shit here. He said I'd been focusing on astronomy, but not the underlying physics. Apparently, one of the main reasons people didn't accept heliocentrism, even after knowing about the phases of Venus, is because the accepted physics of Aristotle had lots of reasons why heliocentrism couldn't be true. Even after Galileo's discoveries of a telescope, He was criticized by many fellow scientists for saying the Earth could be moving. Until I could prove those ideas of Aristotle's physics were wrong, I couldn't claim to have completely refuted Aristotle or proven the model of heliocentrism. But Dad said that could all wait till tomorrow. Mum says Galam and Sid are mounting the crank handle to use to rotate the next bridge now, so we'll be able to cross over to the main part of Wretched Minor in about an hour. Then we're going to spend the rest of the day exploring it. Alright, so something about parallax. I'm not too sure what that's got to do with anything. I mean, you can see what she meant when we were talking about like stars moving relative to each other, right? I think that what we're supposed to do with this is be determining okay, I think I'm missing some. Oh, yeah, okay, so we've got the stars here. Push this button and it lights up particular ones of them. We need to work out which of the order of these stars, and that's what this is here. Now we can, oh wow, we can flip them all the way around. So looking at this, it looks like yellow is actually the closest to me, because it's moving the most. So let's get yellow all the way closer to me. Then I'm thinking red. Then I would guess green, because that distance is shortening. I think that's it. Yeah. Got it. That was a pretty cool puzzle. Yeah, they are just little LEDs. Nice. Alright. Oh god, no, more writing. No? Oh no, this is the second model thing. Okay, so here... this would be the Aristotle Ptolemaic model. Earth, Moon, Mercury on epicycles, Venus on epicycles, Sun, Mars on epicycles, Jupiter, Saturn, stars. And this one here is the Copernican model. Sun, Mercury, Venus, Earth, Moon, Mars, Jupiter, Saturn, stars. So, what do we need to do to get this ladder to drop? What do we have here? Okay, that will let us switch tracks. Okay. So this is supposed to be Venus. So under the Ptolemaic model, this is the one we're currently going on. You can see how when you move across, yeah, it just sort of stays in that sort of track. But if you follow the Copernican model, as it goes around, it becomes full. And then ceases becoming, like it goes back to like its sort of newer status. That's cool. Okay, but I don't know exactly what she wanted us to do here, so let's Venus on the far side to show it into full phase. Okay. So let's put it on the far side to show it in full phase. This does mean on the direct opposite the sun. Yes. Yep, there we go. Sweet. Let's get up this ladder. Alright. Here we are at the base of a radio station. I guess I'm going to keep climbing it. Ooh, haven't seen one of these in a while. Yeah, fuck your box. Ah, a crank. Perfect. We really needed that, actually. There's our boat. So yeah, here we are on top of a radio tower. Bird. And some sort of door. And a cable going to it. Okay. Gonna be honest, wouldn't have climbed this. That's not safe, like 100% not safe. Alright, so now we have to go back. And see which particular thing we're going to use here. Okay, I take it with me, do I? Yeah. Good, because we need to get back up there and crank the other one. If you know what I mean. I don't know what I mean. It's a pretty little island, gotta say. Oh, I think this means we need to fuck with the puzzle up the top as well with the two doors. This one here, am I right? No, we've got to do this one first. Okay. Yeah, that's what I thought it would do. Yeah, that makes no sense for it to be like that, because that hole didn't exist when the army built this damn thing. Did it? So if I remember right, you just have to bring it back around to being in solar eclipse. There we go. Nice. Here we are. This is already here, so we don't have to worry about that or anything. Okay. This is a big island. Like a lot bigger than the other one. Alright, let's check out this watchtower. Some more solar panels. And a big ass cable this time. Okay. Oh. God damn it. Alright. Today we explored the main part of Wretched Miner across the last rotating bridge. We mostly found stuff the army left behind, more shacks and some watchtowers scattered around. There were also a couple more bridges made of steel cables and wooden planks instead of the rotating kind that were still in pretty good shape. Mom figured she'd be able to check them out and make them safe in only a couple of days with help. The first thing Sid wanted to do was get the other zipline working to ride down from the bunker to the main part of Wretched Miner. The ziplines were very sturdy and didn't require much repair, so Mum helped him fix that first. Now that we can crank all 3 rotating bridges, we can make a looping path up to the top of a bunker. Yeah, so you can zipline here, there's a bridge here, you can zipline over here, and there's a bridge on the other side. Okay. Hang on. Up to the top of the bunker, crank the bunker bridge to the zipline we want, open the top floor bunker door leading to that zipline, ride down to either of the other island parts and come back across and up again over and over. It was a lot of fun. Sure. The watchtowers and shacks were connected with long color-coded power cables strung all over the island. You'd think they'd be connected in a simple circle, but the cables zigzag around. One thought maybe it had to do with where cables could be buried or hidden best, or some other mysterious army logic. But decades of weather had exposed most of the cables anyway. They looked intact though. In the shacks we found some diesel generators, but none of them worked. That's probably why the army left them behind. But Galam is good with engines, and he got one running pretty quickly, and he says he thinks he can get them all working again. There isn't just one key that works with all the generators, they all have different keys. Ugh. Mum's not that interested in the generators though. She brought plenty of solar panel arrays in the boat. They soar easily, so we have lots. The shacks also had more of these army electrical switch boxes, and some were wired into the cables themselves, so you have to switch one on to get the next tower powered up, and so on. Mum said something to Dad about maybe using them to make us more secure in some way. He said he saw no sign of anyone being here on this island of wretched miners since the army left, and he seemed relieved about that. But he still liked Mum's idea, so we're going to move most of our stuff again onto the main part of Wretched Miner. July 30. At breakfast this morning, I asked about how Aristotle's physics said the Earth can't be going around the Sun. Dad told me 2 big ways. For the Sun to rise and set, Earth must rotate. But if it did, then every rock of the Earth would be naturally moving in a circle, and that's what ether does, not Earth. Anything made of Earth only ever moved in a straight line towards the center of the universe, which for Aristotle was also the center of the Earth. So his first point here is, yeah, your system doesn't work when I apply my system's rules to it, which is like, okay, buddy. 2, that means if Earth is not at the center of the universe now, then all of the Earth would be rushing in a straight line towards it, wherever it was, at a tremendous speed. This would leave behind animals and such, which fall slower to float in space, as if the Earth zoomed ahead of everything else towards the center. This was because, according to Aristotle, heavier objects, meaning they have more of the element Earth, fall faster towards the center of the universe than lighter objects with less of the element Earth. The natural speed an object falls is proportional to its mass, so a boulder that's 10 times heavier than a small river stone falls 10 times faster. Very disprovable. Very disprovable. That's why they thought heliocentrism wasn't possible. Aristotle's physics said that earthy objects fall in straight lines towards the center of the universe with speeds proportional to their masses, and they could see this wasn't happening. When I drop objects, they do fall straight down in straight lines, and it makes sense that heavier objects fall faster than lighter ones, so I'm not sure how to prove Aristotle wrong. I'll have to think about it some more. Very disprovable, kid. You should have done this in like year 7 physics by now. Dad told me not to be so sure. I'm assuming that they're in year 7 because they're doing with projects and shit. Dad told me not to be so sure, or at least past year 7, that what I think makes sense actually makes sense. The way to see whether Aristotle's physics has flaws is to do experiments, like dropping rocks and seeing how they fall. Looks like I'll have to make actual measurements, what Dad calls quantitative analysis, where you deal with specific numerical quantities instead of qualitative analysis, where you deal with how things work generally without numerical measurements. From a qualitative standpoint, what Aristotle says about falling rocks seems right, but maybe it isn't from a quantitative view. Spoiler, things fall at the same rate. Discounting air resistance. Dad suggested I use a visual way of describing and comparing how objects fall using graphs. On a blank sheet of paper, he drew a horizontal line with an arrowhead to the right, and he said it was an axis that represented time in seconds. He marked the left endpoint of this axis line with a 0, and he said that's the instant when we start measuring in our experiments. He drew equally spaced marks along the axis and labeled them 1, 2, 3, and so on to represent every second after the start time of 0. This is just basically how you draw a graph, guys. I'm sure most of you know this already, but this game, I guess it's not. I guess it's aimed at the same, like at Kai's age. Then he drew a vertical line up from the start of the horizontal axis at the 0. It said it was an axis that represented distance fallen in meters. The bottom of the vertical axis was already marked 0, called the origin of the graph. And he also made equally spaced marks upwards, and they were way too free and so on, saying that it's represented the distance object falls 1 meter. They are American. 2 meters, etc. Dad said I could use graphs like this to represent experimental results. If my experiment is dropping a stone off a tower, I'll draw a starting point of the graph at the origin at time 0, and also 0 meters fallen, because I haven't dropped a stone yet. And after I drop it, if the stone hits the ground 5 seconds later and the ground is 50 meters away, I'll draw another point on the graph at a distance fallen of 50 meters and at a time of 5 seconds. If I made any intermediate measurements of time, distance and time, I could mark them as other points on the graph. It's pretty cool. Here are a few examples I drew for Dad to show I understood. There you go. So, it won't be 5 and 50. It's more likely to be 5 and 30? No. Like, it's more likely to be 50 and, let's see, 50 and 2.5. Because acceleration due to gravity is 9.8 meters a second. So in the first second, I mean, this is really simplifying it. You actually need to do integration to get this to work properly. But after the first second, the rock is traveling at 9.8 meters a second. After the second second, it's traveling at 18.6 meters a second. After the third second, it's traveling at 27.6 meters a second. However, it speeds up. Like you do need to do integration for this to actually accurately measure this. But the general rule is it falls about 10 meters in 1 second, roughly. A little bit less, to be honest. I can understand that the results of an experiment, like 10 different observations, could be plotted on a graph as 10 different points, but the graph only showed distances and times. Objects fall at constant natural speed, and heavier objects had a faster natural falling speed than lighter objects. Aristotle is wrong. And that's what I needed to see. How is Aristotle's idea of natural speed represented on these graphs? Dad said something falling at a constant speed means that over an amount of time, like 1 second, the rock falls the same distance as it does earlier or later over that same amount of time. Like if a rock falls 10 meters in 1 second, then a second later it will fall another 10 meters for a total of 20 meters, and a second after that, another 10 meters for a total of 30 meters. And so on. The rock is falling at a constant speed of 10 meters per second. As I was plugging in these points according to Dad's description, I saw that they could all be connected with one straight line. Dad said that the steepness of a straight line on a graph is called its slope, or gradient. You calculate the slope of a line on a graph by dividing the vertical size of an interval by the horizontal size of that same interval. So for example, 30 divided by 3 gives you 10. Rise over run. Like in the example, for an interval of 3 seconds, the rock falls 30 meters, so the line slope is 30 divided by 3 equals 10. Another way of saying this is 30 meters divided by 3 seconds is equal to 10 meters per second, and that's the speed of a rock. Technically, it's the velocity. I guess you could say it's speed as well, because you're not caring about direction. You can calculate this. The difference between speed and velocity is that speed is a what's the word? Velocity is a vector. Speed is not a vector, because speed doesn't have direction, but velocity does. You can calculate the slope as the total distance divided by the total time, or you can calculate it by taking any small section and calculating the distance in that section divided by the length of time in that section, as they're doing here. Cool. Either way, the value of a slope is always the same for a straight line. When you graph distance and time, the slope is the object's speed, and if the line is straight, the speed is constant. The steeper the slope of a line, the faster the speed. The sooner a falling object will land. The flatter the slope, the slower the speed, and the longer time it will take to land. One can also make a speed-time graph where the vertical axis tracks speed instead of distance fallen. For an object falling at constant speed, the speed-time graph would show a horizontal line. such as this. Since distance is speed multiplied by time, one can get the distance. Holy shit, is this teaching kids how to integrate? One can get the distance fallen by calculating the area of a rectangle represented by the speed multiplied by the amount of time traveled. In my example, the distance fallen over the first 3 seconds can be calculated like this. Yeah, so first rectangle, you can be like 10 by 1. Okay, it's traveled 10 meters. Then another 10, so, 20 by 1, and so on and so forth. This is what integration is, by the way. Basically. Plotting them on a distance time graph, I noticed the graph was identical to the distance time graph I started with. Yep, so derivatives give you this. And I just said integration gives you this. So derivative is calculating the slope of a graph, which is this. Integration is calculating the graph from the slope, basically. It's a bit more complicated than that. Yeah, Dad said this was not a coincidence, and I would fully understand why this happened when I later get to study a kind of math called calculus. Half of calculus is called differential calculus and deals with calculating slopes of distance time graphs. Hey, what do you know? I mean, it's more than just that, but yeah. The other half is called integral calculus and deals with calculating areas under speed time graphs. Again, it doesn't have to be speed time. The two halves are connected in a way that will explain how I got back to the same distance time graph I started with. It's like starting with a number, squaring it, and then taking its square root to get back to the same number. Getting back to Aristotle, he said that if 2 stones are dropped and one stone has 10 times more mass than the other, it will fall 10 times faster than the lighter stone. The lighter stone will take 10 times as long to fall the same distance. Felt like Aristotle was right about heavier things falling faster, but I don't know about them falling that much faster. Here's Aristotle again, beard. Now that I understand how to make these experiments, I want to do some experiments dropping rocks off a radio tower and see what the truth is. So the weight of an object does matter, but it's more to do with terminal velocity. Really? Okay, so this is asking us to find the slope of each of these lines. So the red slope, 60 meters in 6 seconds. So that's a 10. Can I just... Hang on. Okay, it's actually given us points here. YTD. Oh, can I? No. Right click takes you out of it. Damn it. Do these flip around? No, it's actually given us the intercepts. Okay, good. Yeah, this is giving us X and Y intercepts. Okay, so this one is, although it's being a little cagey about it, 4 and 12. No, it's not. And this one wasn't 3 and 30. Oh, yeah, 3 and 30. Yeah, that'd be about right. 4 and 12. If you managed to find the 12 point on this, it would probably intercept with the 4 here. You can also just go 60 divided by 10, so this is going to be 6. Oh, okay. This is my bad. I mean, this one is 6. Don't get me wrong there. Green, 60 divided by 12 is 5. Blue, 60 divided by 15 is 4. And 60 divided by 20 is 3. Now, I think we need to just find the ones where that works. So 30 divided by 3 is definitely 10. 12 divided by 4 is 3. So let's get him down there. 12 divided by 2 is 6. There we go. The others just matched up naturally. Wonderful. That's saving. Yeah, I think this is a pretty good point to end this episode. Now that it's saved. So, yeah, we'll do some more science and reading next time. But in the meantime, I've been Sub. You've been yourselves. Later.